There's a final section in this algorithmic part, fixed parameter algorithms, that I want to briefly mention. It's a nice little trick to combine techniques. Compared to the others, it doesn't improve things by just as much, but it's certainly a simple thing well worth doing. If you ever do this in practice, I think this is going to have an impact. It won't reduce the exponential growth though, but we'll see. That's called interleaving, and the motivation is a bit coming from an extreme case that I'll also show you in a minute. So far, the algorithms conceptually had two phases. We first applied some reduction rules. I called it pre-processing initially, or kernelization if it has specific guarantees. And so then you end up with a problem kernel where everything is bounded in size by the parameter. And then you solve this kernel with a depth-bounded exhaustive search, where here, I mean, depth-bounded really means there's a parameter where you count down, and as soon as that reaches 0, you stop whether or not this instance is solved. Now, why do we not apply this kernelization each time in the recursive call? In the hope that things get shrunk further and we might get a smaller search space. In principle, this might work just because usually the reduction rules somehow involve the parameter. And in the recursive calls, the parameter gets smaller. So the reduction rules might apply further than they did initially. That's the key idea. And let's look at an extreme example just to motivate that this sometimes can help a lot. The example, I'm going to admit at the beginning, the example is a bit made up to make the effect extreme in the way that it's kind of leaving out other obvious things you would want to do in this case. But bear with me for a second just to make the point that interleaving can indeed give you a lot of benefit in extreme cases, and then other cases it'll probably also help, it's just not as obvious. So remember we had where we're still talking about vertex cover. I mentioned vertex cover is the default problem in FPT, where we've already beaten it to death, but there's at least one more substantial result coming next week. And also here, we'll talk about vertex cover again. And we've seen this rule. If you have ever a vertex of degree strictly larger than the parameter, the only option is to take that vertex, because covering all its edges via its k plus 1 or more neighbors is not going to stay below the parameter. Now let's compare two algorithms. The one, algorithm A, is what we've done so far. The catch is we only apply this rule, none of the other reduction rules. And that's a bit stupid, but let's be stupid on purpose to make the effect clear. So only this rule, let me stress that here. So again, you wouldn't want to do this. This just makes the example clearer to analyze. And then we call the same algorithm that we've had before, the simple version, where we just, this was the baby FPT algorithm from all the way back, where we just take an arbitrary edge and say, well, I'm going to include either one endpoint or the other, so I get this 2 to the k search space. Okay, that's the simple FPT vertex cover. And algorithm B is the same idea, same in ingredients, but interleaved. So we modify this algorithm, keep the same basic recursive structure, but we check whether we can remove more high-degree vertices in each recursive call. And so here's some code how this looks like, because it's so long ago. Simple FPT vertex cover here is as we had it back then. Basically some base cases, otherwise we choose an arbitrary edge, and we take the two options. Either of the two endpoints has to be included. And then here we can even be smart and return the larger of the solutions. That wouldn't be necessary for just the search problem. Now the interleaved version differs only very slightly. There's this part here where I just created space. So this part is new. Here, that's the reduction rule, right? we check if there's a vertex of degree strictly greater than k. If that's the case, then we remove that vertex, and that's a concise way to put it. I'm setting the graph to the induced subgraph that I get if I take all the vertices except for this vertex I want to remove. Now I'm remembering in this set C or cover that in my solution I have to pick this vertex V. Right? So if I'm returning at the very end some solution, some vertex cover, then I should include this vertex V. So we remember that, but then also we can reduce the parameter because we've included one more vertex, so we have one less more that we can still include. The rest is the same as on the left, except that here also we include this set of forced vertices. Okay. And now let's look at a very specific family of graphs. I called them lollipop flowers for lack of a not used name. This one's super silly, but okay. So it's a family of graphs, GK, where k is some parameter. And then there's a part here where we have these kind of dandelion-shaped flowers. Let me maybe draw the concrete example for k equals 6. So we have a head vertex here, and then there's k minus 2 stars attached, each with k minus 2 leaves. So it seems like I'm drawing k equals 7, right? So I have to draw this 7 5 times. That's doable. I'm drawing the vertices with different size, but of course they're all in just vertices. Nothing special about them. That's the head. All right, so k minus 2, 1, 2, 3, 4, 5 of these added stars, and each star has k minus 1 leaves, 5 again. And then we attach a tail of 3k plus 1 vertices, so 22. Oh my god, what did I sign up for here? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, got it. This is the tail. Okay, imagine what the graph looks like. Now I'm asking the question, can I find a vertex covered with k vertices? Let's find the minimum vertex cover in this graph. It's not actually that hard. If you start from these guys, it's got to be best to include the centers of these stars, right? Otherwise, I have to include all these leaves. That's going to be worse. So I'm including all those. That also covers all these edges. So these are all done. What vertex is next? What do I have to include in the vertex cover? Yep. You guide me. That one? Yes. Yeah. We have to cover this edge, right? This guy is out because all its other edges are in. And then the rest is pretty boring because now every other vertex has to be included, which will just be all the top vertices. Now, you don't need to count precisely. That's far more than 7, okay? Far more if you want. Now, so that means the instance that we're, I guess I should say, the input is the graph gk and parameter k, threshold k. So all the instances will be no instances, just our poor algorithms don't know about that. Okay, let me copy that. Oh, come on. Good. What do our algorithms do on this example? First of all, I've done the counting for you in terms of the number of vertices. You can count the head, right? You have k minus 2 of these stars, then it's k minus 1 vertices each, plus the one in the center, plus the tail. So we have k squared vertices roughly. If you look at algorithm A, it first applies this reduction rule. Now, the way the graph is constructed, there are no vertices of degree k or larger. So our degree greater k rule just does nothing to this graph. There's no high degree vertices. So because the algorithm otherwise is very, very stupid, it remains at a search space of 2 to the k. And let's make this worst case assumption that we always pick edges from the tail when the algorithm does the recursive, does the random choice, the arbitrary choice. So it'll pick some edge in the tail and include one of the 2 endpoints, decrease the parameter, but it has to try all the 2 to the k options. So the total time will be 2 to the k times the size of the graph to find the edge, or something close to that at least. And eventually it'll answer no, not possible. Our algorithm B, the interleaved version, initially also doesn't do anything, right? And then it picks one edge and nothing happens, and it picks a second edge. So we go down, the recursion tree goes down 2 levels. But at this point, the parameter has gone down to k minus 2. And now suddenly these vertices in the head become high degree vertices. And so in one step, we remove all of them, or to be more precise, we include all of the red vertices, and notice that we already reduced the parameter too much. And so maybe after 1 or 2 further recursive calls, but constant depth, the algorithm can conclude that it's not possible. And this shows you, in this case, you win by applying this reduction rule again, because once the parameter is smaller, it becomes active on a larger part of the graph. Okay? So by and large, we just go a constant number of levels down and we explore a constant search space in this specific case. And so the overall time is essentially linear in the size of the graph. Now, it's a very made-up example. It needs specifically this graph, specifically these algorithms, where we don't apply, I mean, the biggest caveat is, why on earth would you only do the degrees greater k reduction rule and not the one with degree 0 and degree 1 vertices? You would immediately remove this leaf here, and then you would actually remove the entire tail. Right? Okay, but for the sake of the argument, you could have examples like this where interleaving helps a lot. Maybe dandelion would be better. I think that was already taken for some reason. So graph theory people have horrible names, and a lot of them too. Right, the general setup for interleaving. So we've seen this extreme example. What can we do in general? We'll make some slightly more restrictive assumptions than maybe necessary, but this is the part that's nice to analyze. So suppose we have an arbitrary problem, parameterized problem with a kernelization, where now it reduces the problem to a kernel of size q, and that's a polynomial. This is not always the case, okay? But for most of the problems that we've seen, it actually was a polynomial size kernel. At least for vertex cover, we had k squared, I think, as the best. So here, that would be what would be one instance. Right? K squared came from if you remove all high degree vertices and also all degrees 0 and 1. You're left with all vertices between degrees 2 and k, and so you can't have arbitrarily many of them. You can't have arbitrarily big graphs after you remove all of the vertices of high degree. So we need a kernelization that produces a polynomial-sized kernel and does that in polynomial time. That's standard. And suppose we have a depth-bounded search tree algorithm where we somehow split the input into subproblems with some branching vector. So whatever that looks like. In our vertex cover example, this was 1 and 3. You'll see in the next exercises some more fancy versions of that. In general, that's often a way to improve the exponential growth by splitting up into more cases. And let's also suppose the branching itself, so how to make the recursive calls, is computed in some time, and that's also some polynomial in the input size. From this alone, or basically this part alone, we know that the search space has some exponential size. And this base of the exponential growth, alpha, is just this root of the characteristic polynomial, whatever that is for these di. Okay, it just depends on those numbers by how much do we reduce the parameter in each of the recursive calls. If we now think about the variant A of the algorithm again, we first run the kernelization. That takes p of n time and leaves us with an instance of size q of k. Then we, for each recursive call, in the worst case, have to compute this r of n. So we have r of q of k, because q of k is now the problem size. And so that's for the kernelization. That's the size of the kernel. And this is for the branching. And then we have this for each recursive call in the worst case. What happens if we do it interleaved? You can write down general code for this if you want. The general rule would always be, as soon as the input is somehow bigger than what the kernelization produces, right? This q of k, again, is the size of the kernel. Then it makes sense to run the kernelization again. So you run this kernelization and obtain the reduced instance. And then you do the branching on the reduced instance. And you do that recursively. Like this is to be inserted into your recursive algorithm. Now, if you analyze the running time for this procedure with interleaving, it has the same structure. It's also a recursion depending on the parameter. And for each recursive call, you get a recursive cost for the size of the parameter in that recursive call. But now the extra terms, they shrink with the parameter. Specifically here, whenever the input is bigger than this q of k, and that k is the current k, right? That's the maybe most important bit that's not on the slide. That's the current k, or current parameter. By current, I mean in this recursive call, and it's reduced for further recursive calls. That's what's called L here. So we potentially, in the worst case, we have to run the kernelization in each recursive call. That costs time p. But the input size for that kernelization is bounded by some function of L. And also the branching, which takes time r of the input size, is also now a function of L. The current parameter, not the initial parameter. Okay? It looks like a subtle difference that doesn't make any, hasn't any big impact. The non-interleaved version was just this. But it has two kind of implications. One will be it makes the algorithm faster. But to know that or to see that, it means that the analysis becomes a bit harder. Previously, that's why I went over this before we started with this section again. Previously, we could essentially ignore this inhomogeneous part of the recursion. We just pretended this wasn't here, solved the recursion that is left, and then in the end multiplied by this term because it was a constant with respect to L, right? It's the initial parameter, so in the worst case, in each recursive call, you have this cost. Now, with interleaving, the cost of this goes down. So if you want to analyze, if you don't want to just upper bound it by the cost without interleaving, you have to include it in the recursion. So it makes the analysis a bit harder first. Okay. As an example, let's look at the same algorithm we've analyzed in detail before. This better FPT vertex cover, which again was the okay, I think I'll have it on the slide again. So the initial call has potentially a large graph, but then we apply the reduction, Buss's reduction, removing all vertices of degree 0, 1, and greater than k. And so the resulting graph is at most k squared in size. That's the kernelization at the first step. And then we start the interleaving recursive call. Okay, so there's a one-off cost in terms of the original graph size plus whatever we do in the recursive procedure. Okay, so I don't have the code for this again on the slides. It's the algorithm where we split off the case that all degrees are bounded by 2, in which case we solve trivially what the vertex cover is, or we check whether we can solve it with at most k vertices. And otherwise we branch off, but then we have one recursive call where we reduce the parameter by at least 3, because if I remove the case of all degrees at most 2, one vertex has to have degree at least 3. So the recursive cost for this can be written as some base case, and then for the recursive calls, same contribution as before, but now an extra term that captures finding the largest degree vertex and potentially reapplying our reduction rule. And that's both can be done linear in the size of the graph, and the graph is, in the worst case, quadratic in the parameter of the current call. Okay. Maybe for consistency, I should have called this L here, this K L. That's what it was on the previous slide. But of course, it's just a name for the local variable. Now, the point is, I cannot simply ignore this part if I want to get the tighter analysis. So if we dig into this analysis from before, what we did at this point was go from the sequence tk to the generating function. And I'm only roughly sketching the process at this point. So we said there's, I can write this like this and then split off in the recursion after I shifted. So I'm taking out the first few the base cases. I just leave as a fixed polynomial. This was just what was it? Was 1, right? It was 1 plus z squared in our case. And then for the remainder of the sum, I can insert the recursive equation. Maybe let's do it for the concrete example that we have here. So I'm not going to do the full thing. I'm just sketching it up to a certain point. You'll see in a second why or what that is about. So 1 plus z squared. We said just cost is 1 for these small cases. And then for k at least 3, we can insert the recursive equation. And then you may remember or look up, these two parts essentially led to some shifted and modified version of, again, the generating function. Didn't give that a name, t of z. So the green part becomes some, I guess here we pull out one z, and then t of z, I probably have to subtract some. And then there's a z cubed, t of z. And because I'm starting at 3, so this one's probably fine as is. This one needs some subtraction because I start at 3 when the generating function would have started at 1. But what's new is this k squared. Okay, that didn't exist before. We had a homogeneous recursion where we only had as summands these recursive calls, not anything else. But this blue part can also be rewritten because if you look at it now, this is just some specific sum. And you can again look up formulas for this one. Just to give you a hint of why this could be possible, if you take the geometric series where you have z to the k, you may remember that this is just 1 over 1 minus z. Now let's take the derivative on both sides. Sounds a bit crazy maybe. If you do that here though, it's a sum, so the derivative is taken for each summand. And then you have k in front, and then z to the k minus 1. And here we have to take the derivative as well. There's 1 minus z to the minus 1. So if you take the derivative of that, oopsies, is 1 minus z to the minus 2. That's, and the minus in front. That's the outer derivative. And then you take times the inner derivative, which is minus 1. So that minus goes away again. But really what it says is just 1 over 1 minus z squared. And if you take derivatives another time, then you get something that's very close to the term, to the series that we have here. Then you get, I guess here we can actually sum at 1 from 1 because that first term is 0 anyways. That avoids having this negative exponent. So we have the k from before, and then we get another factor k minus 1, and that's z to the k minus 2. So here we can sum from 2 because all the other terms are multiplied by 0. And here you can take derivatives again. So same game, minus 2 for the outer derivative, 1 minus z to the minus 3, and then again the minus 1 for the inner derivative. So you get a similar type of formula for this series. That's not exactly k squared z to the k. It's k times k minus 1, and then there's a shift with z. But maybe with the kind of simplifications or changes of variables that we've done last time, you can maybe get a glimpse of how you can get from this to the blue one. So to cut things short, what you get from this blue thing eventually is just a function of this form. It's some rational function. So it's a polynomial of z divided by another polynomial of z. Let me say capital for functions. So it's some rational function like this, and we'll actually always have a 1 minus z factor in the denominator. Okay? So we don't even need to figure out in detail how this works. That's not the focus of this class. My point is, you can use the same machinery that we've covered for the linear recurrences last time with generating functions. And you can also solve these inhomogeneous equations, where you just need to find a representation for this series. And to be honest, this one you could just type into Wolfram Alpha and it'll spit out the result straight away. For simple cases like this, no need to do it manually. And so if you do that and do it in the general case, you can again get a result that you can just use as a black box. So if you have an inhomogeneous linear recurrence equation of this shape, same as before, but this additional function added or additional term added, and we assume that this additional term is not too big, it's a polynomial, bounded by a polynomial. Then you can show in full generality, if you take, again, this characteristic polynomial, that's actually the same as before. That doesn't quite check out. I don't know. This is probably replaced by this. Forget about it. Then you can get an asymptotic representation, an asymptotic bound for the solution Tn. In terms of Tn0, where Tn0 is the previous recurrence without this inhomogeneous part. Okay. In other terms, what it says, this light blue part here, it doesn't contribute to the leading order growth. It doesn't contribute to the most significant part of the growth of this recurrence if this stays a polynomial. Maybe intuitively it's kind of clear because the overall growth is exponential in n. Maybe it's clear that if you do something polynomial in each step, that shouldn't harm too much. But you're doing it in each step, so you multiply it with the exponential part, so it's not obvious. The trick why it doesn't contribute a factor f of n times this, this growth is that also the added term shrinks if you go down the depth, the recursion tree. So most of the invocations of this fn will be at the bottom level where n is constant. That's maybe the intuition. So, but what it means for you really is whenever you have such a linear recurrence and this additional term, the inhomogeneous part, doesn't grow exponentially, you can basically ignore it. You just solve the equation as if it wasn't there. And the result is at most a constant factor of. Let me comment on, just because it's so nice, a little bit of advertisement for this piece of mathematics. You can push this application of generating functions further. So what we've done was we started in sequence length. We had a recursion for a number sequence. And we wanted to know how quickly it grows because it describes the cost of our algorithm. And from the recursion itself, this isn't obvious. So we translated it to generating function length, specifically these ordinary generating functions. And then used basically algebraic equations in this generating function length to modify what we got from the recursion. So specifically here, the recurrence equation gets a functional equation for the generating function, which you could solve and simplify. Specifically, partial fractions was the magic potion here that did the heavy lifting. So you get a closed form for this generating function where you can, in the best case, extract coefficients back. That's precisely, to this point, that's exactly what we did for the vertex cover example. You can push this further by instead first approximating the generating function. And then you only get back in the end an approximate solution for your number sequence. But oftentimes that's the best we can get because the recursion is so tricky that there's no nice closed form and it's not even clear how quickly it grows from the get-go. But there's this field called singularity analysis. So a singularity in the function, like don't think about AI in this case, it's just a point where the derivative of the function is broken in some way, where the function is not smooth. So it could be, for real functions, it could be a point like if you take the absolute value function, it has a singularity at x equals 0, because if you come from the left and come from the right, the slope is different. And that causes problems for the smoothness of the function. Now, in general, you have to view these functions as complex functions, mapping complex numbers to complex numbers. And then singularities are, in a way, both easier and harder to work with. Complex is always less intuitive, but in a way, the theory is a bit cleaner. To cut this short, you can usually find a single dominant singularity, one of smallest absolute value, and you can prove that this dominates the growth of the number sequence that you started with. So what you do is you approximate your generating function by a simpler function plus an error term, which is a big O term, but of a slightly funky shape. So this is for the limit that z goes to z0, not the more computer science usual n goes to infinity. And then from this shape, there are theorems like the one on the next slide that show you what happens if you take coefficients. If you apply this coefficient plugging operation on this thing, you get the coefficients of f, and suppose that's this, and you get some error term that corresponds to the error term. So I know this is, it's impossible to follow this in detail because I haven't told you what all these things mean, especially singularities we didn't talk about. Just in case you're interested, here's some concrete example of what these transfer theorems can look like. There's a technical condition. It's not so important what this means. If you're curious, I can point you to the right places, or I can tell you offline. If you can represent your function, for example, like this, for some real alpha here, and then the coefficients behave in a nice way. The coefficients of f are essentially the coefficients of g with some error term where you get a polynomial that depends on the power here. Okay. And you can extend this further to solve other kinds of recurrences. That's the gist of it. There's a field called analytic combinatorics that pushed this to the limit. And no pun intended, I guess. Whenever you have a recursive description of some object, probably there's a way that with techniques from this field, you can get an asymptotic approximation of the numbers from the recursion. So just a little bit of advertisement because we delved into generating functions anyways. Briefly back to vertex cover though. Where we left off was with this recursion that described the cost of our interleaved vertex cover algorithm. Now we just apply the black box theorem here. And what we get is the cost is the same up to constant factors maybe as the cost would have been without this f. We just replace it by nothing. But that's the recursion we've solved last time for the number of base cases, which was exactly this 1.4 something to the k. So we get that now the total time is this exponential, no polynomial factor applied to it whatsoever. There was this one step where I said initially the graph can be arbitrarily big. We apply the reduction once, and then comes the recursive part. This is for the recursive part, so we have to add the initial reduction step, but that's all. So we basically transformed via this interleaving technique the cost from exponential search space times a polynomial to just plus the polynomial. Sounds like not such a big deal, but in terms of actual time, it can mean quite a big difference. Okay? And this is, again, the provable worst case. Actual time might be better if you don't always get the worst case recursive calls. The last bit I wanted to mention is that our better FPT vertex cover is not the end of the story so far. People have worked on this more and pushed the exponential growth a bit further down. They also have this plus here, so they're also using interleaving. And so far, this is the best result I could find. It's not clear how far you can push this. It's likely that there is some limit below which it seems there's arguments against pushing further, but I don't think this is reached yet. But the algorithms essentially try more and more cases and more clever combinations. So it gets more and more messy. But in principle, you can push down this recursive, this exponential growth quite dramatically from 2 to the k to 1.2 or 1.3. That's already a pretty impressive result. That's all I wanted to say about this analysis and also the whole of FPT algorithmic techniques for now. A quick summary is what we've seen the two strategies for designing FPT algorithms. One is the depth-bounded exhaustive search, where we use the parameter to truncate recursive calls. And the second was kernelizations, where we shrink the problem size using some reduction rules. And we've seen how we can analyze the resulting algorithms. Now again, generating functions are pretty cool, but if you don't love them just as much as I do, you can use the black box theorems. And all you really need is the characteristic polynomial. And interleaving kind of gives this last twist that really the exponential search is all there is in terms of the dominant cost.